Hello everyone, I'm Pekan Gupta, Solutions Architect at Smart Modular Technologies, and today I have with me Arthur Sanyo, who is the Director of Product Marketing at Smart Modular Technologies. Together today, we will be talking about a new emerging technology called Gen-Z, which is used for memory intensive application. So let's start our discussion here. So let's move to the discussion. Our agenda for the talk today is why do we need these new protocols? What is the comparison between serial attached and the fabric attached protocols? The Gen Z topology as a system, and exploring the Gen Z in detail. And finally, we'll conclude using summary and references about Gen Z protocol. So let's begin with why do we really need an interconnect? And why do we need these new standards? So the data it's growing exponentially. If you look at the IoT devices or you look at the real-time streaming videos, the growth of data has been far more in past few years than it was decades earlier, all combined. The second problem is the growth of heterogeneous computing. Earlier, the compute was mainly general purpose CPUs like x86 processors from Intel and other vendors. But today, if you see, the compute has been spread across GPUs, FPGAs, ASICs, structured ASICs, CPUs, and TPUs. So now the intention is to make them talk together and access same set of memory which contains the data. The biggest and the most important factor of having these new interconnects is the real estate on the PCB. Though we have a lot of CPU sockets added on the PCB, the memory available per core is still the flat. The PCBs on most of these motherboards is saturated. We do not have room to put more DIMM slots. So how do we solve all these problems? The problem is to move to new types of memory interconnects, which are serial attached or fabric attached. Let's look at the memory tiers, which goes back to different types of areas where memory is connected in a system. The L1 and the L2 cache, which sit on the die of the CPU processor, are the closest which talk to the CPU core. The L1 and L2 caches, they have very low latencies in order of less than tens of nanoseconds, but their capacity is also very limited, within few kilobytes or maybe tens of megabytes. Then we have L3 caches. These are the ones which are shared across the CPU cores. The latency increases to 50s of nanoseconds. And similarly, the capacity goes beyond few hundreds of MBs. And with the new technology called HBM, it goes to a few gigabytes. But still, it is not sufficient. This is where the memory is attached outside the package on the motherboard. And that's where your parallel interfaces like DDR4, DDR5, and NVDIMMs come into play. These are the direct attached memories which run in the latencies of hundreds of nanoseconds and provide you with capacities of hundreds of gigabytes. But with exploding data sets, this is even not sufficient. And as we have seen earlier, the PCB real estate is really saturated. So you do not have room to put more DIMM slots on your PCB. So what next? There is a trend to move to serial attached interfaces. These are like PCIe based CCIX interconnect, CXL, or an open CAPI, which is using an OMI based interface. The memory is really not connected, is again connected on the PCB, but sitting far away from the CPU sockets. So you have room to connect more memory modules on a same server. Today, however, our focus is on fabric attached or network attached memories. This is where the Gen Z and other similar protocols like RDMA come into picture. Here, we are talking about moving the memory into a different rack outside the server chassis. So you are accessing a shared pool of hundreds of terabytes or even a petabyte of memory across various nodes. So our discussion is towards the far end, which is the network attached memories. But before we go there, let's do a comparison between direct attached, serial attached, and network attached memories. Let's look at the parallel or the direct attached memories, DDR4s, DDR5s, and NVDIMMs. So the basic bottleneck over here is the real estate. There is no room to add more DDR interfaces. Also, because these are parallel interfaces, any increase in speed, for example, if you move from DDR4 to DDR5 or DDR6, adds more complexity for PCB design. It also increases the cost of manufacturing. So scaling through the parallel interfaces for future is really not a viable option anymore. So what about the serial interfaces? There are many new protocols coming in the serial attached memory. These are OpenCAPI, C6, and CXL. If you look at the various comparison between these protocols, they do similar uh, work. They have a similar approach. They ride on an existing standard like PCIe or any other serial interconnect, but they are backed by different promoters. So OpenCAPI, which is supported by IBM, has a compatibility with OMI interface and is already in production on IBM's Power 8 and Power 9 systems. The controller is mostly ASIC based, and we have an ecosystem with an FPGA based implementation. C6 is another memory expansion and an acceleration interconnect, which is riding over PCI Gen 4 standard. It uses the same PHY and the data link layers of the PCI Gen 4, but creates its own transport protocol or transport layer. The promoters are AMD, ARM, and Mellanox, Huawei, all the big names. It is available as of today and will be productized somewhere towards the end of this year or maybe to 2021. There are some ARM-based systems which support C6, which are available today, but the entire ecosystem or hardware ecosystem is still in incubation and is implemented using FPGAs. What is coming in future is CXL. So CXL is a similar serial attached interconnect which works which reuses the PCI Gen 5 PHY layer or physical layer, and it is predominantly supported by Intel, AMD, and other CPU providers. The availability of this protocol is somewhere down in 2021, and the productization may happen in 2022. And we expect that the early implementations will be FPGA based, followed by an ASIC based controller. This was all about serial protocol. The discussion today is going even beyond that to a network attached memory protocol. This is where you get various other protocol standards, which is like NVMe over Fabric, RDMA, and Gen-Z. Let's compare how the three protocols differ and in their use cases and in their structures. The NVMe over Fabric is mainly a storage protocol because it uses block-based structures. It is a very efficient protocol for cold data storage. That means you just write the data and do not read it often because there are large latencies. It reuses the existing NVMe over NVMe standard and reuses the underlying network protocols like InfiniBand or TCP/IP, UDP to send the data across from one node to another node in the entire data center. There are no software or hardware specific requirements because everything is baked in and it's very matured in the system. Let's compare it with RDMA. RDMA is a similar protocol, but it is primarily designed for large data transfers across or between two applications running on different nodes. So here we are talking about two applications who want to share the data with each other through localized buffers. And RDMA is a protocol which reuses the existing network layers like TCP/IP and UDP to send that data without any CPU intervention. The catch here is you need to have some specialized hardware or what is called a smart NIC, which supports lossless transmission over layer 2 and layer 3 protocols. So you do require some specific hardware NIC to get your RDMA stack up and running in your existing infrastructure. And there are some software requirements because of the specialized hardware, which you need to incorporate in your applications. Coming to a further futuristic approach is Gen-Z. Gen Z is a solution which actually goes beyond the two protocols of NVMe or Fabric and RDMA and improves and optimizes the performance by redesigning the stack from scratch. That means you reuse the PHY and the Ethernet layer, physical layer of PCI and the Ethernet layers, but Gen Z defines its own packet format for MAC and the transport layers. It gives Gen Z a specific benefit of achieving very low latency and high performance for even normal memory load and store applications. To achieve this kind of an low latency and high bandwidth approach, obviously you need a specialized hardware which is designed for Gen Z standard. And you need to have a software stack which supports Gen Z uh, to be plugged into your application. Let's look at the availability and latency and other requirements of these protocols. So NVMe over Fabric is very structured and mature protocol available uh, as we speak today. RDMA is another protocol which is in production, but from some chosen vendors. It's not available or in production from all the vendors. Gen Z is something which is in prototyping phase, and we have development kits and other hardware which customers can use to start their Gen Z enablement or port their application and explore Gen Z and its capabilities. We'll talk about some of these development kits in later parts of the slide. On the latency front, as you know, NVMe over Fabric is more designed for block-based storage. So it has a very high latency beyond tens of microseconds. RDMA, on the other hand, has comparatively lower latency, but it still does not meet latencies of a single or byte-wise read or write of the memory semantics. The reason is RDMA requires the two applications to negotiate on the buffers, have some kind of initialization, and then it is suitable for transferring the data. Second thing, the latency of RDMA is more because of the network layer which it reuses from the existing infrastructure. Gen Z, if you, on the other hand, has the least latency of all three because it redesigns the packet format. It has its own structures and has its own hardware, which is optimized for small data transfers. So as I spoke earlier, the use cases of NVMe over Fabric is cold storage, with, and the advantages are it's low cost and very suitable for backup kind of an application. RDMA is good for data sharing or large data sharing, but you have to have a specialized hardware and you have to have a compatible software to run the RDMA stack. The Gen Z is again optimized for very fast or low latency data transfers, and it also requires a specialized hardware and a NUMA capable software or platform. Let's look at some of these comparisons of direct attached, serial attached, and fabric attached. So as we spoke earlier, this direct attached have latencies in hundreds of nanoseconds. The serial attached have somewhere around 500 nanoseconds, and efforts are being going on to reduce it and bring it down to similar as direct attached. The fabric attached, what we spoke of earlier, has latencies of thousands of nanoseconds or actually 1 microsecond, and efforts are being done to bring it down by half. But you compare the capacities, the direct attached memories, which is like the DDRs, can go up in hundreds of GBs. The serial attached can go in few terabytes. But fabric attached can actually scale to hundreds of terabytes to petabytes. And because the fabric attached brings you a disaggregated architecture where a large pool of memory can be connected to a different rack and shared with different nodes, there is practically no limit of how much memory you can attach to a single system. The efficient utilization not only brings down the TCO of from a user's point of view, but it also decouples the CPU architecture from your memory technology. That means you can upgrade your CPU from whichever platform to another platform, and you can update your memory or reuse the same memory technology with the new CPU platform. So it allows you to have independent cadence of upgrading your CPU and your memory technology without uh, causing any disruption to your ongoing program. So the key takeaways from this slide is direct attached memories are only and only for performance. The serial attached is for scalability and density. But if you really want the advantage of scalability, density, and the cost, the fabric attached protocols like Gen Z are the answer. Now let's look at some of the Gen Z fabric topologies. What you see over here in this diagram is an SoC or an FPGA or GPU based multiple compute platforms which can be from any vendor. They all are talking to a memory devices which are sitting on other side of the network. And this is where the benefit of fabric attached protocols like Gen Z come into play, that they have decoupled your compute infrastructure from memory technology. So you can put any DRAM attached like DDRs, or you can put persistent memory on the other side, or you can have any storage accelerator or a network accelerator talking to your compute node. So the Gen Z fabric allows you to put anything on the other side of the compute platform, and it will still work and talk to your host like a memory or any other equivalent device. These are some of the benefits which I just spoke of about the Gen Z protocol, and it achieves that by dividing the whole system into two parts: the memory controller, which sits inside the CPU or the GPU or on the host side, and the media controller, which sits on the memory side, which is talking to directly to the DRAMs, the persistent memory devices, NAND, flash, and rest of the things. So it abstracts the memory technology, and secondly, it also eliminates the need for tight timing budget. This is a very important aspect because right now, a lot of performance gains are linked to the clock speeds at which you can run your memory. But having a fabric attached memory in between, or fabric attached kind of protocol like Gen Z in between, eliminates the need for having a tight timing budget and gives you more flexibility of upgrading your memory as per your choice. You can actually also offload some of the media specific functions or compute functions on the memory side, giving your host or freeing up your host CPU cycles to do other computational work. So there has been discussion about CXL and Gen Z working together, and I think I'll pass on my discussion to my colleague Arthur for discussing about the working CXL and the Gen Z protocols working together. Arthur?
Thank you, Pekan. Gen Z and the CXL consortiums established a memo of understanding that leverages the complementary aspects of both technologies. CXL and Gen Z are both memory semantic protocols that enable high-speed connectivity to processors, accelerators, and memory expansion, and they make possible a low-latency sharing of memory and storage resource pools among processing elements. CXL focuses on enabling coherent node-level computing, while Gen Z focuses on fabric connectivity at the rack and row level. Gen Z also provides a bridging device to attach external or internal pools of resources. Next slide. So where to start? SMART is supporting a Gen Z micro development kit to help interested companies explore the Gen Z fabric, and we'll talk a little bit more about it. Next slide, thank you. So the Gen Z micro development kit has everything you need to explore Gen Z. It provides a complete setup to perform load store memory access over the Gen Z fabric. It is the smallest and simplest platform that allows for the development and test of Gen Z in-band management and fabric manager software as well as Gen Z memory-driven computing applications. It is optimized for cost, size, and flexibility of fabrics. It also allows for the Linux subsystem development and testing. It has an ARM-based A53 quad-core processing system for load store. It also has flexible cabling types that allow for various topologies. All the Gen Z IP is provided by our partner, IntelliProp. The Linux subsystem and Gen Z driver is published on the GitHub website. The kit configuration and purchase interfaces are provided by Mark. Next slide. So how is the Gen Z development kit used? It's used to aid in the development of the Gen Z software ecosystem, like Linux framework and drivers for Gen Z, including bridges. It's used for host site hardware RTL development. FPGA inside the Orthos card can be used by the CPU and device manufacturers to help develop RTL code for their ASIC. And for the development of advanced Gen Z protocol features like collectives, atomics, coherency, and buffer operation. Through the UDK topology, though the UDK topology will not have the Gen Z switch in between it, but it can give an estimate of load store latency for point-to-point connections on the Gen Z fabric. It is an out-of-the-box reference design for end-use case demo purposes. So please contact Smart if you're interested in getting one of the Gen Z development kits. So to summarize, some of the key benefits of the Gen Z composable memory include lowering the total cost of ownership by increasing utilization of resources, whether it's memory, storage, or compute, across racks and nodes. Lowering the power and cooling requirements as data is processed near the source. And lastly, providing support for advanced functions like collectives and vector atomics, which enable distributed computing operation. Next slide. So lastly, some additional benefits of the Gen Z composable memory include multiple memory modules can be stacked together in a single rack to make a disaggregated pool of shared memory. Each single 1U or 2U rack server can accommodate multiple E1.S or E3.S memory modules, expanding available memory from gigabytes to terabytes or even petabytes, as Pekan mentioned. Memory expansion can be achieved without changing the CPU architecture or adding new DDR slots. Gen Z also decouples the CPU architecture from memory technology, so users can upgrade their CPU or memory at an independent cadence. All this comes with scalability to add memory when needed. We hope you've enjoyed the presentation. This concludes the presentation. And Pekan, if you want to conclude here.
Thank you, Arthur. So this slide has list of various references, webinars, and some of the products which we have in Gen Z. Please feel free to contact us and visit on our website at www.smartm.com/GENZ, and would like to get your feedback about this presentation. Thank you.